Hi, my name's Andrew McLaren, and I want to help you with Lewis dot structures as well as polyatomic ions and resonance. A lot of students really struggle with getting the more complicated ones down here, so I'm going to review some basic ones and then move on to the more difficult ones and how all of the atoms are linked together. And I've got like an hour-long video going over this type of stuff, but this is going to be kind of a short version. So I was working on this stuff with a student, and just to review, if you've got something like this phosphorus and then three chlorines around the center, it looks almost like it might be trigonal planar, but it's actually trigonal pyramidal because there's this lone pair that's above. So you've got four main electron domains, aka like places electrons can be, these three bonds, as well as that lone pair. And so that's going to be a tetrahedral shape, meaning this molecule should be polar. So you might be tempted to do something kind of like this, which would look like a trigonal planar thing, but then the formal charges are not as optimal as they could be. In other words, there's too much negative near the chlorine and not enough near the phosphorus. So chlorine, yeah, it can break octet, but phosphorus right here, it's going to end up having not enough electrons near it when you put a double bond on all those chlorines. I gave a trick question to my student asking them about NCl₅, which is a trick question. Nitrogen does not have d orbitals that it can access because we're talking about like the second energy level. So if you have the third energy level or higher, you have access to d orbitals. So if you had pCl₅, that works. That's acceptable. If you have something that looks like this, like xenon with two oxygens, you might look at that and at first think it's like a linear relationship between those oxygens, but think about it like water. This has got four main electron domains. This will be a tetrahedral shape in general with these two electron domains, and you'll have to recognize that these two oxygens in the molecule are kind of like the two hydrogens with water, and that will be bent. So a little bit of background about like water and carbon dioxide, those can help you have like reference points for visualizing harder ones. In addition to that, I've had students like ask me, do I have to memorize all of the angles between these things? I wouldn't say it's memorizing, I would say it's more of understanding the general like reasoning behind the angles. Because if you've got trigonal planar, that's 360 degrees split into three parts. So that's 120 degrees. So you can reason through that. You don't have to memorize that number. Same with like the 180 in linear. Or if you're in an octahedral shape, you can kind of see how they're 90 degrees from each other. And that should help you out with that quite a bit. Now, if you're talking about like trigonal bipyramidal, you can see that it is basically trigonal planar with two things kind of going above and below it. So you should see the 120 degrees as well as the 90 degrees relative to each other from that. So it's not memorizing, it's more reasoning. Um, and if you have these substitutions of electron domains, I've had many students ask about why that's T-shaped. Um, why we have T-shaped instead of like another trigonal planar. And that's due to these electron domains being slightly wider than a bond, which is a narrow thing. So they need to be further away from each other. And if you had a trigonal planar shape with like 5 electron domains, then you've got those electron lone pairs 90 degrees from 3 atoms, and that's less than ideal. So if you can get it to be bigger angle from more things, then that would be fantastic. So electron domains for T-shaped, they go around that like axial kind of positionings so that they're 120 degrees or so. The only one that you really need to memorize is the tetrahedral, because most people don't know 109 or 107 or 104, which are those angles for if it's more substituted. So that is a little bit of a trick that you're going to need to memorize, but those are the only ones that I have like memorized. The rest of them are more of just like reasoning. So then I started to give the student some questions that are more common and they drive home some points. Oftentimes when you have something written like this, that's indicating how like the atoms are grouped within the molecule. So you've got like 3 hydrogens next to a carbon and then a hydrogen next to an oxygen. This is a bit ambiguous if you're not being clear with how the things are attached to each other. So a lot of organic chemistry, they'll write out the carbons and the hydrogens and how they're kind of grouped. So we've got like methanol and ethanol, which are 2 similar molecules. You'll notice there's a couple trends on how these things attach to each other. Oxygen oftentimes is bound to 2 different atoms with some lone pairs. There should be some lone pairs on this oxygen as well. And carbon is very typically bonded to 4 different things. There might be a double bond, but it's very, very common for carbon to be attached to 4 different atoms. Then we talked a bit about, this is probably, in my opinion, the best tip in the video. Things like this molecule right here, when you have carbonic acid, that can be difficult for people to figure out when they are first doing these types of problems because they want to have like the oxygens chained to each other, like having one oxygen and another oxygen. But if you consider the carbonate ion, the thing once it gives off 2 hydrogens, that has resonance in it. So like, why would you have a double bond on one of these oxygens versus the other ones? Then that helps you kind of work backwards and see like, oh, if I were to attach an H plus, it'd be attracted to these O minuses here. So if you understand the resonance of your polyatomic ions, then that can help you with drawing out these acids that would form them when they give off the hydrogens or dissociate. So if we look at H3PO4, it's very similar. If you think about PO4 3 minus, you can kind of see where those 3 hydrogens need to get attached. And you can also see how there's some resonance that's present there as well. So if you see there's a similarity with carbonate and phosphate and their respective acids, then that's a really useful thing. Same sort of idea with sulfate. You've got the SO4 2 minus ion when you've given off those 2 hydrogens. So if you were to take these 2 hydrogens off, you could have negative charges on those oxygens and there would be resonance. So this type of reasoning helps you with a lot of your polyatomic ions and these acids and what they look like. It's very common for you to have that central atom with some oxygens around it with some hydrogens attached to those oxygens that you can kind of strip off to turn it into its conjugate. That's my number 1 tip with polyatomics and Lewis structures, because once you see the trend, a lot of these problems have very similar structures in them, helping you get some reasoning. Now this one doesn't have 2 oxygens being double bonded to the nitrogen. You can see that in a sense because nitrogen only has 4 orbitals it can access. Like we were saying earlier, it doesn't have access to d orbitals being in that second energy level. So yeah, that's some of my main easy quick tips with Lewis structures lightning round. If you would like more, I've got like an hour-long video going over how to draw these things out. Thank you.